So today we start with the union find problem. We have seen that this problem occurs as a subproblem in the Kruskals algorithm. If you remember, in the Kruskals algorithm, we are maintaining a set of sets. And what are those operations? Given an element, we are trying to find out which set contains that element. So we are maintaining a set of sets which are disjoint. And this is the find operation. Find, say, I. So it will return the name of the set which contains the value I. That is one operation. There was another operation which was needed. If set I and say set j, they are not equal, then you merge these two sets into a single set. So this is the union. So these are the two problems, union and find, given a set of sets. So we will see how to solve this problem in isolation. So let us see what are our assumptions. So C, I will assume, is a collection of subsets where subsets are coming from 1, 2, 3, say up to n. Okay. So I am assuming that the elements of the sets of any set is only the numbers. It is a set of numbers, basically the integers. So what is the condition? Condition is this: union. Suppose I is a set in this set system, so we will call it a system. What is a system? It's a set of sets. So suppose I is a set in the system C. So if you union all the I, that will be equal to 1, 2, 3, 4 up to n. And as I told you, the two sets I and j, if they are different, their intersection must be empty. If I not equal to j, then they must be empty. So these are the assumptions. So what we are looking for is this: there should be a one operation find. So it takes an element I. What is the output? It determines the set I in C with I belonging to capital I. That is the find operation. And there is another operation, union, Ij. This takes two sets, I and j, from the system, and it join sets I and j in C. Okay. So these are the two operations we should be performing efficiently for this problem. Now, what do we mean by the name of a set? So let us be a little bit specific about it. You will see, as you have already seen in Kruskals algorithm, in most of the applications, actually these two operations, find and union, appear like this. So probably one is I equal to find I, then you again j equal to another find, say j. Then the typical operation is, if I not equal to j, then we try to union I and j. So this is the typical applications. Like in Kruskals also we did the same thing. First we found out one vertex, which set does it belong, another vertex j, which set does it belong. Then it is checking whether these two sets are equal. If it is not, then only you basically introduce the edge between these two vertices and union all those two sets I and j into a single one. You make merge the two trees into a single tree. So that was the operation. So this is a very typical operation, and we will see how to support these two operations efficiently. Now let us see how do we represent this set of sets. So here is one representation. So what we will do, we will maintain an array, say C. So we will maintain an array C, and suppose we have the set, say 1, 2, 10, 6, 3. Suppose this is a set of these elements. Then we will represent this set with one representative element. So in this case, suppose I take that representative element as 3. So as if the 3 represents this whole set. So the name of the set is 3. So if I use the array, what it will do, so suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13. So suppose this is an array. The first element, so Ci will contain the name of the set in which I belongs. So 1 belongs to the set with the name 3. So Ci will contain 3. 2 also, C2 will contain 3. Then this is 1, 2, 3, 4, 5, 6. So then 6 again contain the name 3. Then C3 again contain 3. Then we have 6, 7, 8, 9, 10. 10 will again have 3. So immediately if I represent like this, suppose I have another set, say 12, 4, 5, say 8. And suppose this set is represented, the representative element for this set is say 8. So for this one, I will have 8 because 4 is there in the set. 5 will also be 8. Then 8 is automatically 8. Then we should have 12 also 8. And suppose we have another set. Say we have 9, 7, say 11. And 11 is the representation. So 7 will have 11, 9 will have 11, 11 itself 11. So suppose we have, this is the system C. There are 3 sets, subsets, which are all disjoint. So how to represent this using an array? So this is the method. For each set, choose one element as the representative element. Use that index as the name for that set. And Ci will have the name or the index of the set which contains the element I. So in this case 10, 1, 2, 6, 3 all have value 3. So with this representation you can see how much time does it take to find. Suppose I want to know what is the set which contains the element I. So it is not, it's a constant time. Immediately I can find it because then I have to check what is the value of C of I. So find I is nothing but return Ci. So find I in this case will take, so in this representation, so this representation takes order 1 time for find operation. Because find I is equal to nothing but C of I with this representation. But what about union operation now? Suppose you have been given 2 sets. So let us go back to the previous example here. So in this example, suppose the set 3 and set 8 have to be union. In that case, either we have to change the name of all the elements in the set 3 to 8, or all the names of the set, all the elements of the set 8 to be named as 3. Either of this one we have to do to retain the invariance that this is the way we are going to represent. So union in the worst case will take how much time? It will take order n. So union takes order n time in the worst case, because you have to rename every element of one set with the name of the other, and in the worst case one set can be n over 2 elements. So though find operation is very efficient, union operation is not. And remember, we are trying to find out a data structure in which both operations are supported efficiently. Only one supported efficiently is not good. While designing any data structure where certain operations are mentioned, then you are required to design a data structure for which all the operations are maintained efficiently, either constant time or say logarithmic time, which is also good. So that will be our goal. Now the data structure which I just said can be modified a little bit slightly so that we get an efficient time complexity for both the operations. So let's see what are those modifications. Modifications are, first of all, the C array. So probably we will declare this one as an array of structures now. So it has now, first it has one field which is responsible. So this is the array C, array of structures. So the first, this one will have the name of the set for the element I. So Cy for this one will be the set. So I will name this one as a set. Then the second row will contain the size of the set. We will see how we are going to use it later. So this will have the size of the set. Each set will have a size, that is the number of the elements in that set. That will be contained in this second row. And the third is the link. What we will do, each element will be linked to a next element which is also an element of the same set. So basically all the elements of a set now will be linked through a linked list. So Ci dot next will give you the next element in that set, until unless it becomes a probably null. So this is our data structure now. So with this data structure, so let me put what it will look like with our previous example. So this is 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. Now if you go back, let me put the sets again here so that we don't forget what it is. So 1, 2, 10, and 3, 6 is 1, where 3 was the representative element. There was another set 5, 4, 12, then 8, 8 was the representative element. There was another set where it was 7, 9 and 11, 11 was the representative element. So now I'm going to put the names which is as it is previously. So 3, 3, 3, 8, 8, 3, 11, then 8, 11, 3, because 10 is in 3, then 11 will be in 11, then 8, 12 is in 8. So these are the set names as it is previously. Now let me put the next field. So we started, our representative element is 3, so we start the linked list from here, position 3. So this will first point to, say, this one, then this will probably point to this one.
Can't we give just the index of the array instead of the pointer?
I think you can do that too. So when I say it's a linked list, either you can do implement with a real pointer or even with the indexes of the array. Yes, you can do that. So this is 2, and then this will probably go to point to say 10. It doesn't matter. I will point this 1 to 6, right? It doesn't matter. It has to contain all the elements in the linked list. Suppose, so this is the linked list for the set, this set, the set 3. So for the next one, it will start again from 8. So it will start from here. So 8 will first say point to say 12. So 8 will point to 12, and then from 12 we will go to say 5. So it goes from 5, then 5 will go to say 4. So 4, 5, 8, 12, everything is there. So similarly, you can link the set 9, 7, 11. So say 9, 7, 11 will start from here. 11 will go to say 9. It becomes a little bit clumsy with so many pointers. So which one is this? So 11 goes to 9, then 9 goes to 7. So there is another pointer which goes to 7. So these are the all pointers which link all the elements of a particular set. Okay. So now, now I am going to write the two algorithms for find and union. This time what we will do, while doing the union, we will merge the elements of the set which have less elements to the set which has more elements. So what does it mean? Suppose I am going to merge a set of 3 elements to a set of 5 elements, then the set with the 3 elements, their names will be changed to the name of the elements which are, to the name of the elements which is included in the set having the bigger size. So that's the rule. So you are not going to arbitrarily merge the two sets. The set with the less elements will be merged to the set with the higher elements, larger size. And you will see this trick, this particular trick, which is very easy to do because we will be maintaining a size field. We can check the size of the two sets. So this particular trick suddenly gives you a better complexity. You should already start thinking why it should give you a better complexity. Okay. We will come to that claim and we will prove it, why it is. So first, I didn't tell you how to maintain the size. So the set with the 3, this will have the size 5 because there are 5 elements. Set with the 8 will have 4 elements, and set with the 11 will have the 3 elements. So these are the fields. All the other entries will be say 0 or something. You represent that they are empty. It doesn't matter. Yes.
Instead of doing the pointers like that, we can do like for every set, we can have a dummy pointer to each and maintain separate linked list for each. I mean, for 3, 3, 3, 3, 3 in the place, you just have a dummy pointer to a linked list, and then maintain a linked list separate.
That's what is doing also.
You're making it very clumsy. Like
So yeah, it's only in picture. Inside the computer, they are not present. These links. This spaghetti is not present inside the computer. So it's fine whether it is clumsy or not. But implicitly you are doing the same thing. It's the same. It is the same linked list you are mentioned. Whether I draw a separate picture for a linked list or not, it does not matter. Okay. So let me see. So how do we write this function? So function find I. So this is very easy. What should be the code for this? Return ci dot set. That's it. That is your function for find I. Just look at the index which is stored in C of I with the field set. That will give you the set name basically. Now comes the procedure for union. So procedure, let me write this one in a separate slide because otherwise I will not have enough space. So procedure union I and j. So these are the two sets which we are going to merge into a single one. So first we check if Ci dot size, which one is less than Cj dot size, then basically exchange I and j. Exchange means just the value of I and j are exchanged. So what does it mean? I will always contain the value which is larger, because if Ci dot size is less, then only do this. So I will be larger always, all the time, larger or equal to. Now you change the size field, Ci dot size equal to Ci dot size. So I will be basically the name of the new set now, as we told, because I is a larger set, we are going to merge the smaller one to the larger. So I will be the name for all the elements now. So Ci, and the size field has to be changed also. So Ci dot size should be Ci dot size plus Cj dot size. You maintain the size field for later operations. Okay, here now I am going to change the names for all the elements in the set J. Okay, for this one I need to do this. So second Ci dot next. So Ci dot next will tell you what? Ci dot next will tell you the next element which is going from its representative element. It's not. Ci dot next, yes, it is that element, it will give that pointer. So second is there, that's why it is called second. Okay, and now Ci dot next is set to the index j. So this will basically point, j is the index for the representative element for the set j. So Ci dot next is set to that one. So Ci dot next now starts from the list, now starting from its own element to the list which is representing the j. So once you do that, then we go to a loop t is equal to j. We don't have to, that doesn't matter in the algorithm. Loop ct dot set equal to I. Okay, the next one what I am going to write, you will see that is nothing but changing the name of all the elements to I. That's what we are doing. If ct dot next is equal to 0, 0 means basically null. This 0 means null, the pointer is null, there is nothing. Then ct dot next equal to second basically. So that is the last element in the list. For all the other elements you put the value I. This can be verified, what it is doing is basically exactly just changing the name properly. Exit the loop, oh sorry, so this should be in the if, so this is exit the loop if it has happened, and if, and t is equal to t dot next, and this is forever. Forever means basically the loop is going. I am not writing in a do while fashion. So this part, this looping is basically going through all the elements of j, that is t dot next, that's the linked list traversal, and changing its name to I. That's what it is doing. And this is just when you reach the last element, you just put the last pointer to the second pointer which previously was pointed to by ci dot next. So you basically this will do merging the two lists into a single list. But remember, while merging the two lists into a single list, we are changing the names for the ones which has a smaller size, which is very important for our analysis to show that this operation is nothing but log n. Okay. So this is the algorithm. Now you can see in the worst case how much time does it take for one union n by 2 or order of n. In the worst case, one single union still takes order of n times. So we have not improved anything. Previously also find I was order 1 and union was order of n. Here also find I is order 1 and union is also order of n. Then why did we do all this? The gain is in a amortized complexity. The gain is here. So that is the claim now. So now we are claiming, suppose you do n minus 1 union or n union, it does not matter, n minus 1 union operations takes time only order n log n. See, if each union operation takes order n time, so n minus 1 operations, if we do calculate by that rule, it should be order of n square. But this claim is saying if you take n minus 1 such union operations, total complexity is not more than n log n. So on an average, that means or amortized complexity of each union operation is log n, because n operations are taking n log n. Okay, what is the proof for this claim? The proof for this claim is, in a nutshell, is like this. Each time you are changing the name of the smaller size set to the bigger size set. So, and the complexity over the n operation is nothing but guided by the total number of name changes, because that's the time consuming part, the name changes. Now each time an element changes its name, it finds its position in a set which is at least twice as large as the previous one, at least. So mind my language again. Each time one element changes its name, it finds its position in a set whose size is at least twice as large as the previous one. So how many times you can each element can be touched, or each element can be changed its name? Only log n, because every time it will find its space in a double the size set. So only log n times, and since there are n elements, total name changes is n log n. So that is the logic. Why the n operations will take order n log n time, not order n square. So I am going to write it. Consider the size of the set that contains the element I. Define some sigma of I equal to C find I dot size. So sigma of I is basically its size in the current set. So sigma I changes whenever I is touched in the union operation. In this case, the new sigma of I is at least twice as large as the old one. Just what I said. So this is why, this is, I am going to write in the next slide, this is because I is touched only if it belongs to the smaller of the two sets. So define now K as the number of times element I is touched. Touched means is changing its name. Then we know this is true. Sigma I is greater than equal to 2 to the power k, because every time size is at least doubling. So if k times it has changed, then sigma of I must be greater than equal to 2 to the power k. So therefore k is less than equal to log of n. So, and this gives you the proof basically. N minus 1 operation will take n log n time. So this is very important that we merge the smaller one into the larger one. You will see that the entire logic breaks down if you do the other way. You cannot argue anymore. So you have to do very carefully with respect to size. And see, merging in this way it's not that costly. We have to maintain only the field called size, nothing else. And maintaining that field size is also very easy. Just merge the size of the two, add the size of the two into the single one. So we know now n minus 1 union operations take n log n time. Each find I takes order 1 time. So how much time then with this data structure implementation for union find, how much time does it take for Kruskal? You remember Kruskal's algorithm? So Kruskal's algorithm now takes how much time? If you remember, in Kruskal's algorithm we have, so suppose G has n vertices and m edges, then Kruskal's algorithm had m extract mean. It had m extract mean, then it had m find, right? Then it had n minus 1 at most union operation. Go back to Kruskal's algorithm, you will see exactly this. You will first put all the edges into a heap, then you will extract the edges one by one from the mean heap and check whether two vertices belong to two different sets or not. So that will give you m find operations, and if they belong, you merge them into one tree, and that edge goes to the minimum spanning tree also. And since minimum spanning tree can have at most n minus 1 edges, so I will have at most n minus 1 union operations, not more than that. So with this one, what is the total time complexity? It will be order m extract mean will take m log of m plus m find will take m, and n minus 1 union will take n log n. So your total complexity will be order m plus n log of n, because this m is superseded by this m log n. So I can take out m from the order, and then m plus m. And can somebody tell me why I can replace log m by log n? M is always less than n square. So at most it is m log n square, but n square is also log n because 2 comes as a constant factor. In log you can replace m and n, but not if it is not log. M square, n square is different from n, but log of n square and log n are same because it's a constant term comes before log. So m log m I can write m log n, so I get m plus n log n. This becomes the complexity of your Kruskal algorithm. And probably you cannot avoid this complexity because anyway you have Kruskal algorithm require the edges to be sorted with respect to their weights, and you cannot avoid m log n there itself. Now let us see how can we improve further the complexity of this union find problem. How can we use some other data structure so that this complexity comes down?
So, same data structure, instead of the set name has 333 everywhere. Instead of interpreting 3 to be the name of the set, we interpret 3 as the place which holds the name of the set. So in that place, in the place 3 alone, you change the name. So it takes order one time.
So for that one, all the elements must have a pointer to that place. So his question is this: instead of all elements having the name 3, all elements point to a place where you keep the name 3 only once. But now the problem is, instead of changing the names, now you have to change the pointers. Suppose the
In the place 3, the array position 3, you will have the name of the set, which can be changed to the bigger set's name.
yes, now the problem is, suppose you maintain you union I and j into a single set. So I, all the elements was pointing to a single location, then j, all the elements in j also are pointing to a single location. You will go and change probably j to I. Now you have 2 locations for the same name.
Yes, but so it doesn't matter.
It matters because it grows. It grows. Then the next time you will say 2 and 2, it will give 4 names. It goes on.
But still it takes only order one time to find
It does not take order one time because as it is growing and growing, ultimately probably there will be n places where you have to change all this. Just try to see initially, suppose all the elements are pointing to a single place. When you merge the 2 elements into a single one, you are changing the name in one. So you have already 2 copies of the same name. Now you change these 2 elements with another 2. You are changing in 4 places. So it is the same thing. Okay, so yes, that was a very good suggestion, but unfortunately it does not help us. By maintaining a pointer, again we have to take keeping the copies. So the same problem comes. So we will see in the next data structure, which we will take in the next lecture, how can we make this data structure more efficient, so that we have find operation a little bit costly, not too much, but our union operation, even the worst case time, will be log n. So that will be our next data structure for the same problem.